Today, we're going to talk about combustion reactions. So, a combustion reaction is no different than any other chemical reaction. And so, last week and throughout this week, we've been talking about how to balance reacting systems. And so, homework 3 is predominantly combustion, reaction separators, all sorts of reacting system material balances. So, a combustion reaction is no different than any other chemical reaction. And the only reason why we highlight it as a different type of thing is because it has specific nomenclature that is more conventionally used in combustion than it is in other processes. Right? So when we're burning stuff, typically we're not burning a high value chemical. So if you're in a chemical plant and you're burning something for energy that you know what it is, it's either going to be something super simple that's a waste product like hydrogen, methane, ethane, something that we can actually characterize as natural gas. But in general, what we're burning is the garbage, right? It's the garbage we don't care about, right? It's just for energy. So when it comes to oil, when it comes to coal, gasoline, diesel, jet fuel, we don't actually know what all the molecules are in those systems. And we don't care what the molecules are. All we care about is how much do we burn, how much energy do we get out of it, and are the products that come out, are they safe and are they clean? Right? So in the case of diesel, that involves making sure that you're scrubbing out all that sulfur and nitrogen so that you don't get a lot of really bad air and things like that. And so that's why when we talk about combustion reactions, sometimes we have to think about the problems a little bit differently because we're not actually dealing sometimes with specific reactions. In a lot of examples, we will be talking about specific reactions, but sometimes you'll say, I don't know, it's 86% carbon, whatever percent hydrogen, and we're just burning it, right? And so we can still do all of our techniques, like atom balances. These are going to be really useful for combustion reactions. So a lot of what we're going to be talking about today is just clarifying what do we mean by specific terminology that is unique to combustion reactions. So nothing special about the reactions themselves. You can, in theory, think of them as just normal reactions, but they have their own nomenclature system. So in general, when we talk about combustion reactions, we talk about carbon plus oxygen going to CO2. We have hydrogen plus oxygen going to H2O. We have nitrogen. That typically just goes to N2. That's the most stable state. So thermodynamically, we don't want NOx, right, which is what makes air brown and gross. It's along with sulfur and NOx. But in general, the combustion reaction is you go to N2. Sulfur goes to SO2. That is the stable configuration. These are complete combustion reactions. So when we're burning something, or we're doing any real process, in this class, we're kind of ignoring all of the real physics of what's going on inside of the process. We're just saying we're magically separating or we're reacting it somehow, but we're not concerning ourselves with how these actual reactions are being done. And so the way to think about combustion reactions is we take a fuel, right? If we're burning coal, it's going to have carbon, hydrogen, nitrogen, sulfur in different ratios. Yeah?
That one's not balanced at the end yet.
Yeah, let's get that one. Or we can say 1/2. So in these combustion reactions, we can think of it as a specific reaction, like we're burning methane and oxygen to make, CO2 and water, right? And we all know how to balance those reactions. But another way to think about it is let's just take our fuel, explode it into individual atoms, and then rearrange them into these products here, right? On paper and mathematically, we don't really care what's happening in the real world, and so in many ways, it's best just to think about your system as burning the individual atoms themselves. Thermodynamically, right, and you guys talked about state functions in thermodynamics, it doesn't matter your path. Well, enthalpy is a state function. So the enthalpy that's released when you burn something, that's the change that's going to happen no matter how you do the rearrangement. So thermodynamically, we can disassemble every feed fuel molecule into atoms and then reassemble it into the combustion fuel products. And so when we're dealing with a fuel that we don't know the composition, this is what we have to do. When we're dealing with a fuel where we do know the composition, then we can balance it following kind of the traditional approaches that you're used to from a chemistry class. Now, the last reaction here that always seems to throw everyone off is incomplete combustion reaction. Carbon plus 1/2 O2 goes to CO, and this is incomplete combustion. CO is very bad for a number of reasons. Can everyone think of one good reason why it's very bad? It's poisonous, right? CO binds to, I think, the hemoglobin, so you can't actually transfer oxygen throughout your body if you breathe in carbon monoxide. What's another bad reason for making CO? It is polar, but you're wasting energy. You can still burn CO by giving it another half an oxygen to make it CO2. Right? CO2, the reason why we make CO2 in water is because these are two extremely stable molecules. The bond energies between carbon and oxygen and hydrogen and oxygen are extremely stable. So the more CO bonds that you can make, the more energy you're pulling out of the system. And so all of combustion operates on the fact that carbon-hydrogen bonds are a much higher energy bond than carbon-oxygen bonds. And that breaking of the bond and remaking a smaller bond means there's an energy surplus. That energy goes somewhere, and it goes into heating up the gases, making a flame, radiating out to heat stuff up. Right? So that's the basic fundamental thermodynamics of it. So CO is very bad. So every time you're doing a combustion reaction, these four are the main ones that you care about. Right? When you're trying to calculate how much air you need to burn your fuel, only these four. Carbon monoxide, we throw it in every once in a while as sort of to make the problems a bit more complex. Right? Because if you do have CO being formed, you know something's wrong. So these are our combustion reactions. Now, in terms of nomenclature, one of the most important ones that we talk about is called excess air, or theoretical air. So I'll call it air/O2 required. And these are a couple of terms that we just have to sort of commit their definitions, somewhat arbitrary in some cases. But first term is theoretical O2. So the theoretical O2 is the amount of oxygen required for complete combustion. If we don't have enough oxygen, we are going to be forming carbon monoxide, which is both poisonous and wasteful. But when we do our calculations for theoretical O2, we only consider these four complete combustion reactions. If the problem statement says that CO is being formed, it does not impact your theoretical O2. I don't care how much CO is being formed, theoretical O2 is an arbitrary definition for only the complete combustion reactions. Even if CO is formed, it doesn't impact your theoretical O2. And I 100% guarantee I will have a lot of questions about, well, I don't get why this number is here, this number is there. Never consider CO in theoretical O2. It's always the ideal scenario. You also have theoretical air. And this is the same thing but for air. So the same idea here is that how much air do you need to provide the oxygen required to burn these fuels? Right? The atmosphere is free. Right? You don't have to pay for air usage. You can use as much air as you want to. Right? Rejecting chemicals into the air, that's a different story. But taking air in, there's an endless supply according to how much a chemical plant is going to use. So you pull in air to typically burn all of your fuels because it's free. Oxygen, pure oxygen, is not free. So theoretical air is how much air is required to provide the oxygen necessary for complete combustion. And then we also have excess. So we have excess O2 or we have excess air, right? The idea behind these is exactly the same. So this is moles in excess. typically percent moles in excess of the theoretical amount. Right? You think of this exactly like an excess reagent. Right? You say, oh, we're feeding, chemical B in 20% excess because chemical A is the expensive one. Same thing is going on here in the way too. Right? Air free, fuels expensive. So we want to add in a little bit excess air. So what are the downsides of not having enough air? Well, we're not going to have complete combustion. What are the downsides of adding too much air? Can anyone think of some downsides? Yeah.
The ratio will be off for your reaction, so you could actually have it become an
Inhibitor. So these reactions will progress pretty well regardless of how much oxygen there's in there. But it's possible that if you have so much oxygen, it's like that lower flammability limit problem, you could actually prevent a sustained flame from existing. So you'll still have some reactions occurring, but those lower flammability limits are the limits of a violent and, you want violent when you're having a flame, but not when you don't want to have a flame. So if you want to have a reaction that propagates, you need to have a certain concentration, yes. So you could purge it well below the concentration. What else could happen by having too much air in the system? Yeah?
You're taking up space that you could fill up with something you can react.
Exactly, right? So you have too much, then your reactor has to be really big. What's another complication? Yeah?
You have a buildup of nitrogen or like another gas?
If you have a loop, if you have a recirculation, yes, you can have a buildup of inerts in the system as well. What else? Any other ideas? One big one is it gets colder, right? So when you break the bonds, right, these are the reactions that give you energy. Every single time you burn a carbon atom to make CO2, right, that gives you a certain amount of energy. That energy has to be released and it goes somewhere. Typically that goes into heating up the temperature of the gas that's participating in the reaction, right, or the product gases. Now, the more air you have in there, the more molecules there are to absorb that energy and the lower temperature increase you get, right? Because when you're calculating a delta T, right, it's the number of moles times by the C sub P times by the delta T. So as you jack up that number of moles, your delta T goes down and down and down and down and down, right? So flooding it with way too much air, you won't get a hot flame temperature, right? So what do you think is going to have a higher flame temperature? Burning something in pure oxygen or burning something in pure air? Oxygen, right? Because that's nitrogen. This just steals energy. That's all it does. It doesn't participate, right? It's not helping out with the reaction. It's just stealing energy. Okay. So how we calculate the excess air? This is going to be equal to moles fed minus moles theoretical divided by moles theoretical. Now this is a fractional excess. If you wanted percent, you would just have to times it by 100 there. But this is the same exact concept of an excess reagent, but we're using specific terminology of excess air.
So when it says moles in the feed, is that total moles or moles of O2?
This is the moles of either air or oxygen being fed. Okay, another really important concept . So one of the complications of combustion reactions is that we're dealing with real air. So the air in Utah is different than the air in Southeast Texas, where a lot of refineries and chemical plants are. Right? What is a big, big difference between our air in Utah and the air in Texas? Yeah?
Humidity.
Humidity. Now what is humidity?
Water in the air.
Water in the air. Water in the air messes things up for our calculations. So oftentimes we care about the difference between the composition of the fluid on a wet basis, which means with water, and dry basis without water. Right? Certain analytical techniques, it's easier to keep track of the carbons. Right? The water changes based on the day, the humidity, and so the water amount can throw things off. And a lot of really easy analysis techniques, they give you the dry basis. So you basically measure the composition of everything that's not water in one set of experiments, and then you measure the composition of water in a different set of experiments. Right? So when you're analyzing these for practical purposes, we have to separate these two measurements just because that's conventionally what's done. So on a dry basis, so if we look at air when it's dry, now we typically approximate this as 21% O2 and 79% N2. Now this is not strictly accurate, right? There's a lot of other stuff that's going on in the atmosphere. So the actual composition of air is about 70, let's split it in order same way, about 20.99 O2, 78.0 N2, 0.94 argon, 0.03 CO2, and 0.01% everything else. So it makes sense that we approximate nitrogen as 79% because in general nitrogen is inert. Oxygen is typically what we care about for air, and we can do a pretty good approximation with the 21%. But argon, CO2, all the other stuff, we lump it in with the inert nitrogen. Now this is the dry basis. So the ratio of oxygen to nitrogen to argon to CO2 is typically going to be fairly constant, right? Unless you look at the long time scales of global warming, right? But in general, right, these ratios are going to be consistent. But day to day, location to location, you're going to have different amounts of humidity. So in humidity, and we'll be calculating how we actually do this, but for now, fully humid air is approximately 3% water mole percent. So fully humid air, the difference between feeling like you're in Utah and it's not humid and muggy versus dying because you're sweating so much is 3% of air, right? But the rate at which your skin can evaporate water is dependent on whether or not you're fully saturated. So it doesn't matter how small it is, right? 3% is the difference between humid air and dry air.
Quick question on
yeah.
the actual percentages. The very bottom one, is that
Oh.
0.01 or 0.00?
0.01, sorry, didn't make that dot big enough. And this is like hydrogen, xenon, helium, all sorts of other gases. So we know that the mole fraction Y is equal to the number of moles, in this case if this is water, number of moles of water divided by the total number of moles. So in this case here, we use nomenclature saying NH2O divided by N of dry. These are all the dry gases. So this is everything here. Right? So we use this terminology for the N, the number of moles of dry gas, plus NH2O. So if we say that this is equal to 0.03, and we say that N dry is equal to 100, right? What is another word for this? This is called the basis, right? We're assuming a basis of 100 moles of dry gas to do our calculation. We can then calculate that NH2O is equal to 3.1 moles. Now, right now, we have air on a dry basis. So if we now convert that to air on a wet basis, right? In this case here, on the dry basis, if I have 100 moles of dry gas, I know I have 21 moles of oxygen and 79 moles of nitrogen. But on a wet basis, this is the N total is your wet gas. So instead of dividing by 100, we're dividing by 103. Small difference, but when you have a combustion stream, you have a lot more water. So the wet and dry basis becomes more significant when you're actually looking at the effluent. So the composition of air on a wet basis is Y of oxygen is going to be equal to 21 divided by 100 plus 3.1, which is a little bit different, 0.205. 4, not a huge amount. Y of N2 is equal to 79 divided by 100 plus 3.1. And this is equal to 0.766. And we've already said that air is 3%. Any questions on a wet versus a dry basis? The only thing that's changing is what your total number of moles is here for when you're calculating your mole fraction. Yeah.
So in the top right-hand corner, when you did n dry equals 100, is that saying so there's no water in that air? Then if that's the case, why did just to the next right, directly to the right of it, you wrote that there were 3.1 moles?
This is the solution to this equation here. So if we assume a basis of 100 moles of dry gas, and we know that water is 3% of the total mole fraction. So what I've done here is I've written out the definition of a mole fraction. The number of moles of the species you care about divided by the total number of moles. The number of moles of dry gas plus the number of moles of water gives us the actual total number of moles if I have a jar of wet humid air. And so then I just solve this equation here for NH2O based on this being 100 and the mole fraction being 3, and it turned out to be 3.9. Does that walk you through it? Perfect. Yes?
So you said that fully humid air is about 3% water. So how do they calculate like the humidity percentages? Like 96%?
So we have a whole like week of humidity. So you're going to be really thrilled about that. So relative humidity is how close you are to the saturation point, right? So that's what we care about, right? Because the rate at which our sweat evaporates is not related to the absolute concentration of water in the air. For us, we don't really care about that. So in the news report, it makes more sense to report relative humidity, because if I'm at 40 degrees C, or sorry, that's really hot, 40 degrees Fahrenheit, right? That's so cold that less water, right? This is going to be at like, normal temperatures. But as it gets hotter, this value goes up. As it gets colder, this value goes down. And you use a thermodynamic equation called Raoult's law to help us calculate that. Who's heard of Raoult's law? A few people. Yeah, so we'll talk about Raoult's law a lot. So you can calculate this through thermodynamics through a really, really simple equation, right? It's not hard to calculate at all. But the relative humidity is what the actual concentration in the air is divided by the maximum. So this is the maximum. This is the saturation limit for standard kind of room temperature air. But as you get hotter and hotter and hotter, let's say you're in Thailand, it's like 110 degrees Fahrenheit, you might have closer to 4% water in the air, or in Texas, it could be, 3.5%. Yeah.
I was just going to ask, is saturation based on temperature?
Yeah, but the relative humidity, right? So if I were to take air in Utah that is 100%, if I took air in Utah and I were to take it in a jar and raise it up the mountain as we got colder and colder and colder, my relative humidity would go up, but my absolute humidity would stay the same. Because the relative humidity is a function of the temperature, and that temperature tells you what's the maximum amount. But yeah, we do a lot of humidity. Don't you guys worry. We're going to cover that one. We're getting so sick of it. All right, so we're going to do something. We're going to do an example now. I think example is kind of the best way to teach this. Let's see how we want to do this one here. So first we're going to do an example of excess air. So excess oxygen and excess air are kind of sometimes used interchangeably, and the key thing is just to know, are you getting your oxygen from the air, or are you getting your oxygen from pure oxygen stream? Sorry, I stopped working for a bit. All right, so let's look at the combustion of propane. C3H8 is propane's formula, plus some unknown amount of O2 is being required, and we know that we are forming CO2 and H2O. How do I know that we are only forming CO2 and H2O? Because it's a combustion reaction. How do I know that? Yeah.
It's complete combustion.
It is complete combustion. So let's look at our equations up there. Propane is made of what two atom types?
Carbon.
There we go. That's a very simple one, yep. So carbon goes to CO2. Hydrogen goes to H2O. So can we use this as a tool to help us balance the reaction? So how many CO2s do we need? 3. How many waters do we need? 4. 4 times 2 is 8. 3 times 1 is 3. So that's an easy way to balance combustion reactions. Look at the carbon for the CO2. Look at the water for the hydrogen. And then now the oxygen is the last step. So we need 6 plus, let's see, we have 6 here, plus 4 is 10. And that gives us 5. Now let's also quickly balance out the incomplete combustion reaction. C3H8 plus an unknown amount of O2 goes to CO plus H2O. This doesn't change, right? Hydrogen is still going to be the same. Carbon's going to be a bit different. So we have 3 less oxygens. That's, I think, 4, 7, so 7 halves. Right? So if you have insufficient oxygen, you're promoting the formation of carbon monoxide, which is a bad thing. All right. So if we were to have an example here, let's say I'm feeding the process with, well, I have it here in units of mass, but we're running low on time. So if we're feeding 20 kilograms of propane and 400 kilograms of air, I already did the unit calculations here, so it's kind of a waste of time. 0.453 kilomoles of propane, I'm just going to call it P, and 13.8 kilomoles of air. So the question is, do we have enough air, not enough air, too much? What's the percent excess? Right, so we're going to do that calculation right now. So first, let's do our theoretical air calculation. So what we're basically asking for is blank kilomoles of air being equal to 0.453 kilomoles of propane. And we're going to do like a unit conversion thing, but I ran out of space. So we're trying to figure out how much air do we need to fully burn 4.53 kilomoles of propane. Well, for every 1 propane, we need 5 oxygens. So 1 kilomole of propane is equal to 5 kilomoles of oxygen. And for every 21 kilomoles of oxygen, we have 100 kilomoles of air. And if we calculate this out, N theoretical air is equal to 2.27. Oh, sorry, I did this in units of oxygen, not air. So we don't need this step here, because I don't have the number for the air. We have it for oxygen. 2.27 kilomoles of O2 is required. So if we look at our air, we have 13.8 kilomoles of air. We can break that down into oxygen and to nitrogen. So this corresponds to 2.89 O2 and 10.9 N2. So do we have enough oxygen to burn this propane? So we're feeding in 2.89. Our calculations tell us we only need 2.27, so we can calculate a percent excess. So our percent excess is going to be following our equation, moles fed minus moles theoretical divided by moles theoretical. We're feeding 2.89. Our theoretical is 2.27, 2.27, and this is equal to, if we times it by 100, to go from fractional to percent, 28% excess. So we're adding in a good amount of extra air. Yes?
Should that conversion be 5 kilomoles of air per kilomole of propane?
It could not actually, because
Oh,
in our
so-
reaction here, we're working with the oxygen.
Okay.
But if we were to repeat this calculation with theoretical air, you would get exactly the same number here. Because I would be timesing this term here by 100 over 21, and then I would be using this number here. So it actually works out to be exactly the same if you want to think of theoretical air or theoretical oxygen. Right, so some professors in our department do something called oxy-coal combustion, right, where you actually burn coal in an oxygen-enriched environment, in which case you can get a hotter flame temperature, which means you can have a more efficient boiler, and since there's less nitrogen, the effluent gas stream is more CO2 enriched, so it's cheaper to capture it and sequester it. Right, so in that case, this wouldn't hold true, the 2179, if you're doing some sort of a specialty oxygen-rich burning process. Just got a neat area to connect it to some research that's going on in the department. All right, last little bit of time. We're going to go through this propane example, but we're actually going to balance out the process. Same units here. So we want to know the outlet composition. And I'm not sure we'll have sufficient time to run through it, but we're trying to look at it on a wet and dry basis. Okay, so if we were to draw this process, we have 0.45, I'm just going to truncate it a little bit, propane, 2.89 oxygen, and 10.9 N2. And these are all kilomoles. Coming out, we sort of have an unknown amount of propane, we have an unknown amount of water, and we have an unknown amount of oxygen. So for this particular example, we're going to say that our constraints is you're generating 1 kilomole of CO2 and 0.429 kilomoles of CO. So this is actually, let's say we measured partially the outlet stream. And so what we're going to do is we're going to balance this whole process. What do we think is the best tool to balance this out? We have extent of reaction, we have atom balances, and we have molecule balances. What should we use?
Extent of reaction.
Extent of reaction. So I have one vote for extent. Do we have any other votes for other techniques? Atom balance. Does anyone recommend a molecule balance?
No.
I would not recommend molecule. I would recommend atom balance on this one because if we do extent of reaction, we have 2 reactions that we have to keep track of. Right? That adds in an additional degree of freedom, an additional equation we have to worry about. So I would recommend that atom balance is probably the easiest way to solve this problem. Right? How many unknowns do we have? 3. How many independent atomic species do we have? 3. Carbon, hydrogen, and oxygen. So we can do our 3 atom balances to balance this process out. Which one should we start off with? Carbon. Why carbon? Is there any carbon in this unknown?
No.
Is there any carbon in this unknown? So we only have one unknown that has carbon in it, right? So if we do out our process, all right, C balance. So coming into the system, we have propane, 0.45 propane. For every 1 propane, how many carbons do we have? 3 carbons. Leaving the system, we have 1 CO2. For every 1 CO2, we have 1 C. We have 0.429 CO. For every 1 CO, we have 1 C, plus an unknown amount of propane. And again, 1 propane equals 3 carbons. So this is kind of shorthand. I'm kind of truncating the units a bit. So if we calculate this out, we find it's about 0. It's not exactly 0 because there's some round off error and truncation about how we did the calculations. So for the exam, atom balances should be this quick. It should be lightning fast. You should look at it and be able to do a mass balance or an atom balance really, really quickly. Or writing out the number of moles using the extensive reaction approach. These should be second nature, no hesitation type things. Okay, what's next? What should we do? Hydrogen or oxygen? All those in favor of hydrogen, raise your hand. All those in favor of oxygen, raise your hand. Looks like the hydrogens win on the vote, and I recommend hydrogens as well, because oxygen is in both of these molecules, which means we know we're going to have two unknowns. So we'll do our H balance, in which case coming in, we have 0.45 propane. For every one propane, we have how many hydrogens? 8 hydrogens. Leaving the system, we have our water. And for every one water, we have 2 hydrogens. And that gives us a flow rate of water of 1.812 hydrogens, water's coming out of the system. And then lastly, we'll do the oxygen balance. We can write this one out really quick. So coming in, we have 2.8902. For every one O2, we have 2 O's. Leaving the system, oh boy, we've got a lot. We've got our water, and this is just a 1 to 2. We have our oxygen. Again, this is a, this is a 1 to 1. I'll that in there. We have our CO2, 1 CO2, and again, this is a 1 to 2. And we have our CO, and this is a 1 to 1. It's a what? 0.429, 0.429 CO. And we do this all together, and we get 0.7702, and this is all kilomoles. So we've balanced our process. Any questions on the atom balances? This should be how quickly you should feel comfortable doing atom balances, because when we get to a more complex system, this is going to have to be sort of the trivial first step. Yeah?
So we have nitrogen going into the system. Where's the nitrogen coming out?
Oh, I just kind of balanced it in my head. 10.9 and 2. So what type of balance did I just do there? Molecule balance. Right? Nitrogen is not reacting. So I can just do in equals out on a molecule balance because the generation and consumption is 0. So in my head, I just quickly did that molecule balance. Because you know the nitrogen is just floating around. It's not doing anything. All right, last thing really quickly. How I set up the last step. So now we just need to do the wet versus dry basis. I won't have time to fill in the numbers before all of you get too antsy to enjoy your weekend. So I will just set up the table of how I visualize doing this. And it makes it really easy to convert between wet and dry bases. So how I set up the table. Right? When we look at the outlet, in combustion reactions, we typically call this the flue. Flue typically refers to burner outlets. Effluent typically refers to a general reactor outlet. Right? So the effluent of a general reactor or the flue of a burner. So what I typically do is I write down all of my species, CO2, CO, O2, N2, and then at the very bottom here, I put water. Now the reason why I do that is that when I have my flow rates, I can fill in the numbers for all the flow rates just based on what we calculated here, right? 1 CO2, 0.4 COs, 10 nitrogen, so on and so forth. Right? We just fill in those numbers. And then down here, we have a total summation. Now I will do this for the wet gases, which includes water, and summation of all of the dry gases. And so from these we get N wet and N dry. So you can imagine building this in a spreadsheet, right, where you just click on all of them and say summate, right? So you want to do that for everything that's not water, that's your dry gases, And then for everything with water, that's your wet gases. So you'll have a total number of moles of dry and a total number of moles of wet. So then when you calculate your mole fractions, Y wet and Y dry, all you're doing is taking NCO2 dividing by N wet, which you're getting from adding everything up. And for dry, you do NCO2 divided by N dry. And then, of course, for water, you don't have an entry for the composition on a dry basis because you've excluded it from the calculation. Yes, question?
This is even when you get water out of the reaction for water and products?
Yes, you could do a wet basis for any type of gas. It doesn't have to be a combustion gas. Now, when you're dealing with combustion of something like methane, methane produces a really wet effluent. Right? For one carbon in methane, you get one CO2, but you get two waters. And that's different from the reactions that I've had with propane. Right? So the ratio of water produced to CO2 produced is oftentimes why they say methane is a clean fuel as opposed to coal. That all has to do with the carbon to hydrogen ratio. Most of the energy that you're burning is stored in those CH bonds. The CC bonds don't have as much energy stored in them, and they produce more CO2. So if you want to produce the most energy for the least amount of CO2 being generated, methane is your best choice. But it has nothing to do with how dirty or clean or anything it is. It just has to do basically with the H to C ratio, the ratio of carbon to hydrogen. You want the hydrogens, you pay the consequences of the carbon in terms of greenhouse gas emissions. All right, have a great weekend. See ya.